Hello everybody. Today we are going to continue with the sets, which is a topic in discrete mathematics, and this is going to be part 2.4. Again, this video lecture is presented by Star Academica. You may reach Star Academica by sending an email to staracademica@gmail.com. We'll be very happy to answer your questions or look at your suggestions. Okay, what are we going to learn today? Identities for set operations, examples, proofs of identities and equalities, collection of unions, intersections. First, we get started with set theoretic equalities. There are some identities which are always true, so let's see and understand them. If we have a set X and we unite it with itself, we get an X. This is quite trivial. You are putting the same elements into the same set. You are not getting any new elements, so you are back to the original set. And if you are to intersect X and X, again, the intersection will be X. These are called idempotent laws. Commutative laws, we can interchange X and Y because they are always equal, whether we are taking unions or intersections. So it is up to us which one to prefer when we are working on these problems. Associative laws, we can first unite X and Y, then unite it with Z, or unite Y and Z, and then unite this with X. You'll get the same result. Similarly with the intersection. Okay, and we should be able to remember these things from, say, addition for real positive integers. We had the same property, associativity. One can add 2 and 3 first, and then add to 5. Or add 3 to 5, then to 2. As we see, if you're adding 2 and 3, this is 5. 5 plus 5 is 10. So it's easier to do this computation compared to this one. So it has some advantages. Okay, next we have distributive laws. We can distribute union over intersection. So this is going to be, if you have X union Y intersects Z, X union Y intersect with X union Z. Or if you have intersection over union, X intersect Y, union, X intersects Z. So these are the same. Next, before we proceed, let us make a note here. So far we used X bar, X overline for the complement. However, in some books, even here, we are going to use sometimes a prime notation, X prime, for the complement. Okay, what are the identity laws? If we are to unite any set X with the empty set, we get itself, so nothing new is coming into X. So empty set with respect to the union operation behaves like the identity. That's why this is called identity laws. Okay, and if we again say, take B, part B, if we unite X with the universal set, so this is everything in the universe, the huge set, we get the huge set, we get the universal set. So nothing X will be contribute to the set U because everything is inside the set U. What about part D here? If we are intersecting a set X with the U, I get an X back. Okay. Complement laws. If we are uniting X with its complement, okay, we get the universe set. If we are intersecting X with the complement, we get the empty set. Why? Because X and its complement are disjoint. They have nothing in common. If we are taking the complement of X, again, we apply the complement, so we get X back. And x difference y is the set. We can rewrite this as x intersect y complement. So is this really the case? Let's take x and y. Okay, and what is x difference y? It is this part. Assume that we have a universal set. Okay, so x, what is y prime? Y prime is anything outside of y. If we are to take this y prime, the complement of y, intersect with the x, you see this part is x difference y. So this makes sense. This is true. Okay, so far so good. Okay, we have De Morgan laws. These are very important. In the logic, they're very important. Here also they are important. If you have a complement of x union y, the complement will take the complement of everything really. So this will be the complement of x, and the complement of union will be the intersection complement of y prime of y. So when we are doing complements of union or intersections, here it is the intersection, we take x prime, we change intersection to the union. If it is union, we do it intersection, and y prime. It's easy to recall these important laws. And the final law is the consistency principle. If x is a subset of y, then if you unite x with the y, nothing new comes into y, you get the y. So again, it's y, and vice versa. If x union y is y, x must be a subset of y. Again, if x is a subset of y, then x intersect y is x. So this is the x inside of y, right? Okay. So if you take the intersection, what happens really? We get x again. We get the set x, because it is inside. Okay. So far, so good. Let's give a proof of De Morgan law. So this is one of them. Okay, there are we'll see three methods to give proofs. Okay, and the first one will be with the element. But when we are working with the equality of sets, we have a very important property from the logic part. So if you want to show that C is equal to D, then it is good enough. Actually, it is necessary and sufficient to show that C is a subset of D and D is a subset of C. So we have two parts to study. So, okay, let's get started with the first one. We'll try to show that A union B complement is a subset of A complement intersection B complement. So we take an x, an element from this set. What does this mean? X is not in A union B by definition. Okay, so here it's very important. X cannot be in A and X cannot be in B, right? Otherwise, X would be in the A union B if one fails. So we have an AND here. Okay, so what does this mean? X is in A complement and X is in B complement, which means X is in A complement intersect B complement. So we have the first part. Now we'll prove that A complement intersect B complement is a subset of A union B complement. Okay, again we take an element from the left hand side. So if an element is in the intersection, it has to be in both. So X is in A prime, A bar, and X is in B bar. So X being in A bar means X is not in A and X is not in B. So again, remember this part here. We want to move to the union. Then if X is not in A and if X is not in B, so X cannot be in the union of A and B. So then X is in the complement of the union. So we have the second part. Okay, so we are done with the proof. If we combine this two, we have what we wanted. Okay, and for a homework, you may try similarly to prove that the complement of A intersect B is A prime A complement union B complement. If you follow the same similar steps, you'll get the result quite easily. Okay, given two sets A and B, and there's a theorem property that A intersect B is equal to B intersect A, which is called commutative property. So let's give a proof to this one also. Okay, so if we take X inside A intersect B, then by definition, X is in A and X is in B. So this goes both ways. It is necessary and sufficient. If you have the right-hand side, you get the left-hand side. If you have the left-hand side, you get the right-hand side. This comes by the definition of the intersection. Okay, now what can we do? We know that the AND logical AND is commutative. So we can switch these two statements. Okay, so this is the same as equivalent to, this means also equivalent to X in B and X in A, again by the commutative of now the AND, logical AND operator. So this means by the definition of intersection that X is an element of B and A. So actually we are done. Okay, now we have another property. This is the distributive property, and this time we are going to give another way of proof. The proof will rely on membership tables. Okay, so we take this A, B, and C, quite similar to the logical tables. Here there is a slight small difference. Really, Z0 will stand for the false. Actually, in the set theory means it's not an element of A. That's what it means. So it means 0. 1 will be true. That will be X is an element of A, say. So here we see this means that X is in B, this X is not in A, and X is not in C. So B union C, this 2, for example, I'm looking at the second row, B union C will be 1. This is like OR notation. Okay, so this is AND notation, this is OR notation. So we can do the computations. Let's look at a couple of them. For example, 0 and 1. What about A intersect B? So if it's not in 0, if it's not in A, it is in B intersection, it's not in the intersection. If it's not in A, not in C, it's not in the intersection. Okay, so B union C, it's in B, it's not in C, it is in the union. Here we go. So now what do? We see that A intersect B union C, for this particular choice, it is the same as A intersect B union A intersect C. So we have how many cases? We have 8 possible cases. So let me take another example, like A and B, okay, and C is 0. So element, element, not element, true, true, false. What is B union C? It is 1, because it's in B, it's not in C, it's in the union. What is A intersect B union C? So if you are intersecting these two, it's in A, it's in BU, and B united C, so it's in the intersection. That's 1. What is A intersect B? 1, 1, it is 1, perfect. What is A intersect C? 1, 0, then it is 0. So what is union of these two? It's 1. So they are the same. They agree. So we do these computations, and we can complete the table easily. Okay, here we go. We have the table, and if you look at the column here, with this column, they all agree. So they are the same, they are equivalent, and we have an equality between these two statements. So we are done. This is called membership table method for proving sets equalities or sets identities. Another example, another way of proving that this, which is A union B intersects C, the complement of A union B intersects C is just C complement union B complement intersect A complement. This time we are going to use the properties of the operations, the well-known identities that we have listed before. So we start with the left-hand side. Since this is a complement thing, complement of A and complement of B, if we are using the Morgan law, what happens? We have A complement, intersect, union becomes intersection, and we have B intersects C complement. Okay, first thing. Second thing, we want to reach this conclusion, we can apply the Morgan to this part only. So B complement, intersection becomes union, and C complement. So far so good. They don't look the same, but they are close. Okay, now commutativity or union. So we switch B complement with a C complement. Great. And finally, we switch A complement with this part, which is an intersection, by using the commutative or the intersection. And we see we have the right-hand side gotten already. So we are done with the proof. Okay, next we may have more than two unions or intersections. For example, if we have the set A, B, and C, like this, and the union, what is the union? It is this three all together. You put them together, and intersection will be this tiny part which belongs to three sets, to all three sets. Union collection of sets. We can have n finite sets, call them A1, A2, AN, and the union of these sets from 1 to n can be easily represented by these special symbols. So we have a big U for the union, start from 1, I, this is the index of the sets, so AI, up to the n. Similarly, we take the intersection of n sets, and we use the big cap to represent this intersection. Let's look at an example. The set AI is I plus 2, I plus 3, I plus 4, and it continues up to infinity, keeps repeating forever. And the first question will be, what is the intersection of these three sets? So we need to understand these sets first. What is A1? A1, we start with the 1 plus 2, which is 3. And I plus 3, it's 1 plus 3, which is 4. And this is fine, so we have A1. A2, similarly, whenever we see 2 for I, so we put it here, it's 2 plus 2, it's 4, 2 plus 3, 5, 2 plus 4 is 6. And A3 similarly will be from 5, 6, and 7. So the union of these three, if we pay attention carefully, this guy starts from 3 and goes to infinity, so it contains A2, so A1 contains A2, and this contains A3. So this is the largest one containing everyone, so the union will be A1. Good. Now, if we are to combine everything, I mean A1, A2, and A3 with A4, what happens? So A4 will start from which number? 6, right? 6, 7, 8, it will go to infinity. So again, will be quite similar to the first one, so the union will be A1. But if we have n of them united together, the result will be A1. Okay. We have the same set, IIIs, but this time we look at the intersection of these three. Okay, so what happens? We need to go back and remember A1 was starting from 3, right? 3, 4, 5, up to infinity. A2 is starting for 4, 5, blah, 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 and A3 is from 6, so the smallest one, sorry, from 5 is A3, from 5, 6, 7. And if we have A4, this will be A4. So if we are intersecting, n of them, the smallest one, which will be an. Okay, we may have infinite collection, then this is the notation, and after nth step, we put 3 dots, meaning it continues forever. And here also, we can intersect infinitely many sets, and the notation is quite similar. We put on here an infinite symbol, which represents the infinite collection or intersection. Okay, here is a set AI, the ith set, and the question is, what's the union of these three? So what is A1? So this will be 1 over 1. So it stops at 1. A2, we have 1 over 2. So we start with 1. So goes up to 1 over 2. So this is A2. And A3 will start from 1 over 2 up to 1 over 3. And if you take the union of these three, we get A3 contains. What about the infinity though? So now we can look at this tree. If this is not good enough, it doesn't give you an idea, you can put A4 and think about it. But it should be clear that the union starts from 1, goes to some ith step, but it does not stop. It goes to infinity. So this is how it's going to look like. Now what about the intersection of these three sets? Let's go back. You have this, this, and this. If you are intersecting, you getting A1 is the smallest, it's inside, so you get A1. If you take infinitely many though, nothing changes, so again you have A1. So for the infinite intersection, you have A1 also. Okay, let's look at another example. We are supposed to find the union, infinite intersection of AIs, where AI, so we'll have a couple problems. This is the first one. AI will look like a minus I plus 1, up to minus 1, 0, 1, blah, blah, blah. So we need to understand these sets first. Always, we first write down the very first steps, like A1. What is A1? It's minus 1, 0, 1. A2, it's minus 2, minus 1, 0, 1, 2. Okay, hopefully this is going to give some idea. So A1 union A2 will be from minus 2 integers up to 2. So which is A2, right? So A1, so A2 contains A1, right? So if you are taking the union, it's A2. So if you are taking the union of all possible such sets, what happens? So we keep A3 will be from minus 3 to 3 integers, A4 from minus 4 to 4. So up to infinity means from minus infinity up to infinity. So this is the whole integer set. Okay. And what about intersection? This is a little bit down, so I'm going to take it up here. So what if you take these two intersections? Because since A1 is inside A2, the intersection will be A1. A2 is inside A3, right? This is how it works. So intersection of all AIs will be the smallest one, which is A1. Okay. So A1 is this set. So that's the intersection. Another example where we have AI, which is minus 1, 1. It's a 2-element set. And the A1 will be minus 1 and 1, A2 minus 2 and 2. So what's the union? You put them together, all of them. We are missing 0, so it is integers minus 0. What about the intersection? A1 and A2, they have nothing in common, so the intersection is empty. Okay. Another example. This time we need to be a little more careful. We have a closed bracket, so it means what? This means that this is a real part of a real line, right? From minus I up to I. So we have infinitely many numbers, elements here. So this is the interval -1, 1, a2 minus 2, 2 closed interval. So this is the real line. We're going to get help to understand visually what this sets means. So this is the set A1, right? This is the set A1. This is the set A2. As you see, A3 will be from here to here. Great, this is the A3. A4 will be from here to here. So what's happening? A5 gets larger and larger. If you take the union of all of them, what do we get? We get the real line, everything. Okay, what about the intersection? This was the first one. The second one was this one. The third one was this one. So it keeps enlarging, but if you intersect, it will be just -1 and 1 interval. That's the smallest. Another example, from -I to infinity. This is also an interval. Okay, and A1 is -1 to infinity. -1 is included. -2 is included. It's closed. Okay, here is a real line. So this is A1 from -1 to infinity. Starts from here, goes up to infinity, keeps going. A2 from -2, A3 from -3, A4 from -4, and for any n keeps getting larger and larger. So we are taking the union. What happens? This is going to be the real line. So what about intersection though? So intersection, this was A1 from 1 to -1 to infinity, A2 from here to here. So the intersection is A1, which is this set. So that is A1. This is going to be our last example. Again, we are supposed to find unions. This time also we have an interval. This is a little more interesting, maybe a little bit more challenging problem. So let's look at this carefully. Again, in order to answer this infinitely many unions, we have to understand the sets first. If n is equal to 1, then we have 1 plus 1, 2 over 1, 1 over 2. So this is A1. Okay, from -2 to 1 over 2, that's the interval. And A2, plug in 2 for n, it's 3 over 2, minus 3 over 2, and plug in 2 for n, it's 2 over 3. So this is A3. A3 will be 4 over 3, minus 4 over 3, and 3 over 4. So we are not going to list anymore. To have an idea, we go to the line, real line. So A1 from -2 up to 1 over 2, you see, this is A1. A2 from -3 up to 2 over 3. A3 from -4 up to 3 over 4. So if you are to take the union, really, the very first, the largest one was -2, but -2 is not included. And this keeps going to the right. So every time, please pay attention to this one. This is less than 1. So it's closing to 1. However, it's never 1. So we can take the limit and understand, you see how it moves, the blue one, step by step. It moves to 1. Okay. So in order to understand the right-hand side, the limit is 1. So which means it's going closer and closer, never reaches 1. And the very first one -2. So it is this open set. And what about intersection? Let me go back here. Again, what is A1? A1 was this guy, to 1 over 2. And A2 was this one, right? And A3 was this one. Okay, now these guys from the left are getting closer to what? What is the left-hand side? If you take the limit of n plus 1 over n with a minus, as n tends to infinity, this is -1. So from the left, we are approaching -1. From the right, we need to be careful because the right one, what's okay, since this is the intersection, we are going to take the smallest. So that is this one. So intersection will be like this. So minus 1 and 1 over 2. That's the intersection. Minus 1, it is included, not excluded. Why? Because minus 1 is in all the sets. It's an element here. It's an element here. It's an element here. We are pushing from the left, but every time it is inside all of sets. So this is included. It's minus 1 closed, 1 over 2 open. 1 over 2, it's never included. Okay. 1 over 2, it's not included in A1. That's why it's not. It is included in A2, 2 and 3 in all, but it's not an element of A1 because it is an intersection. It has to be open. So this is the result for the intersection. Okay, this is all for today. Thank you for watching this video lecture. For more problems, solved problems, homework problems, you can visit this webpage. And if you have any questions or suggestions, please send an email to this Gmail account. See you in the next lecture.